Guys, today we are going to learn about how to use an Openfoam software to solve a problem of having a geometry engine streamline flow with an external flow. We will be considering a problem of elliptical cylindrical cylinder in the uh, streamline, and we will be using GMesh as a meshing tool and Openfoam software as the solver for this problem. This is the problem. This is the content of our video. First, we will create a geometry and mesh. Second, we will be learning about how to use boundary condition and solver settings. Third, how to run solver, and then the post processing process we will be going to learn. First, then we will first we will define the domain. It is rectangular in shape. Then we will create an elliptical cylinder having center at 4,5, having minor axis along the streamline. Then with this 2D geometry, we will be going to make a 3D geometry using extrude command. Thereafter, we will going to generate physical surfaces and volumes and also name the boundaries. Then we will generate a 3D mesh using gms to form command. Now we will be going to look how it goes on. So first, let me clear this. And now we will be creating a new folder for this. First, this is the terminal of Ubuntu to how to use open the its folder. First, we will create a folder for that. Now we use Gmesh to generate geometry. This is the interface of the Gmesh. First, we will create a domain using your points. First point will be added as 0, 0, 0. Then I am going to add as 15, comma 0, comma 0, 0. The second point. Next, third, I am going to create a point of 15 plus 10, and fourth point as this 0, comma. These are the 4 points. You can see in this, these are the 4 points that is being generated. Now we will create a line. And how to create a line, just go to the toolbar, select line, and then as you can see in this, select the start point. First I'll select the start point, then I'll select this end point for the line. The line get generated. Similarly to this. Now we have generated our domain. Now we're going to generate our ellipse. For this, first we will consider a point as 3, 5 is this point, then a point 4, 5, then 3, 5. Now 3, 6.5, 3.5. Now as we generated this, uh, Now we will create an ellipse using ellipse arc. First, we will select the start point, then the center point, and then the end point. Wait. Start point, center point, the axis point, and this is the end point. Similarly, the start point, center point, major axis point, end point. Similarly, the start point, center point, major axis point, end point. Now, as we have generated this a 2D space, now I will use the extrude command to translate it to the Z and Z direction. Wait, before this, we will create a surface, this and this. As you can see, this surface has been generated. Now we will use extrude command to translate it this and this. As you can see, this the 3D geometry has been generated. Now we are going to use we are going to add the physical surfaces. First to this, considering this as an inlet. This is a front. This is the back. This is the top surface. This is the bottom surface. This is the outlet. Now we will name the surface of the ellipse. The surface is ellipse. And now this is this surface. Now I am going to add the first. Now this is the volume. is fluid here in our case. Yes. Volume has been first we will add a volume to the surface, the fluid. Okay. As you can see there, that volume has been generated. Now we will create a 3D mesh. Um, just 3D mesh. As you can see, the mesh is uniform throughout, but we need to get a fine, more finer mesh across this ellipse. So we will be going to decrease the mesh size at this as across 0.75, 0.75, 0.75, 0.75, then save and then reload. Now you can see that it's ready. Let's make it more finer. And as you can see, this more finer mesh across this. Now we will export this as an Gmesh. Gmesh ellipse, ellipse. Now we have generated this mesh and exported the file. Now we'll go back to this and you can check there that this it is yeah, this is the name dot message. Okay, the file. Now we will go to we'll close this Gmesh tool for as of now. Now we will go to the tutorial software. Now, well, these are the folders that is being in the tutorial. Now we'll go to the incompressible uh, folder. So the incompressible is the fluid we have chosen is the incompressible instead. Now we will go to the CD Openfoam. Now we will go to the cavity, CD cavity. Cavity. These are the folders that is present in this cavity folder. Now we will make a copy of this CD cp-o. This is the command to copy the folder from one point to the other. cp-o folder name cavity to the path home 1D desktop mm, conform ellipse. Now, as we can go here, and we can see this file has been generated. First, we will copy this outside the folder and we'll be deleting the constant folder. It will get generated afterwards after doing this. These are the properties of the pressure property, and this is the velocity property of this field. Now, as we have done this, now we will be going to copy the mesh file from our geometry to cavity folder. This is the generated mesh file. Now we will make use the gmesh this command to make a 3D mesh. Gmesh to form. First gmesh. First exit cd. Okay. What is the file name first? Elliptic sim generated. As we can see, this is that this. Now go to this folder. As we can see, this has been generated. We will copy this again to the folder, constant folder. Now we will learn about how to put these boundary value conditions in the our mesh and how to use this. So these are the values that pressure at walls will be of zero gradient, outlet fixed value of uniform value 0, and at sides it's empty. Similarly, in for velocity at wall, no slip condition is there for sides or there is a no is an empty, and inlet a fixed value of uniform 100. So let's go and do this. Now we will go to this boundary condition and change. We will remove this instead of patch. We will put our conditions for this. First, this is the boundary condition. So first we will put it as it empty. Similarly, back will be type empty as it is a wall. I will remove this. And top it is a wall, so which will it's an empty. Inlet it is a patch, and outlet it's a patch. We will remove this and this. Bottom it is empty. It is a patch. Since it is also a wall, so we will put it as empty. save. Now first we will copy this for a problem. Now we're going to put the first p-values. See, as you can see this, we will add this to here, and now we'll be customizing it. Need first, instead of moving wall, we have zero gradient at front and back, so it is empty in front and back. At top it is zero gradient. Inlet, it is fixed. Pressure, is it it's a fixed value at inlet. Let me check this. At pressure, at outlet a fixed value. Size and volume is at inlet, it's empty. Bottom, zero gradient. Ellipse, it is empty. Default faces. We will remove these, as we do not require these boundary control fields. And similarly, we will do this to velocity profile. At fixed wall, it's a no slip condition. It means for your top, bottom, front, back, it's a for top it is no slip, inlet. Now we will this is it. Inlet, it is a fixed value, as we can see here. It is a at inlet, it's a fixed value of uniform 1, 0. So we will put it as a fixed value uniform. Bottom, it's fixed bottom. We are having here, it's a wall type, so we are having no slip. Ellipse, we are having no slip. Now we will remove these. And this. At outlet, Okay, we have not entered the outlet, so we'll add the outlet. Outlet type fixed value value as uniform 0. I'll save this. Have we have done this for no? So I will be adding outlet as type outlet. We are having 0 gradient. This Control S. Now we will check mesh. This error in front line 20. There's an error. Let me check it again. Boundary conditions in front. So sphere empty. You gradient at this ratio. Now to remove that error, we are going to do gmeshing again so that we can get this. Just gmesh to form, and as we can see that the mesh has been generated again. Now first we will copy this to the constant folder. Now we are going to change the boundaries as the front is the wall, back as the wall. We will remove the physical type. Top as the wall, inlet as the patch, uh, add outlet as the patch, inlet, bottom as the wall, ellipse as the wall. Save this. Outlet as the patch. Now we will copy this. If required, we can use this. Now we will go to the point 0 for establish the boundary condition for pressure. As you can see this, fixed wall, it is in 0 gradient. It is top we are having zero gradient, at inlet we are having empty. As we can see this here, that velocity at wall is pressure is in walls is zero gradient, and outlet it's a fixed value, uniform value is zero, and sides is this. So we will make it this is front and back is wall, so we are having zero gradient front. It's an empty sides, it is an empty side sphere. Now we will go with the u part, velocity part, that is in front we are having no slab. At outlet, velocity is no slip at outlet. Mesh is okay. Now we will go to the solver setting. Now we are going to learn about how to run solver and the post-processing process. Okay, so we will go with this. Then now we'll select, as you can see here in the folder, system. We are using Openfoam as the flow is incompressible, so we will use this, and time step is 0.05. Now I'll say Openfoam. There's an error in this. Okay. 956. 956. Mm, 921. 921 is this. Okay, there's no correct basis after this. And again, still